In March this year, we released KisanSLM, which is a small language model trained on farmer queries, which was uploaded on AI Kosh. AI Kosh is a sovereign AI model and dataset repository created by the Ministry of IT for Indian datasets and models. And a model has received some amount of attention, but last week a contract hit was carried out on that, and I received an interesting feedback.
Dear sir, I want to give you my usage feedback.
So this was 750 words generated by ChatGPT. I even asked him if he had done that.
Yes sir, I am using ChatGPT Codex suggestions.
And then he sends me a presentation, a 20-page presentation, again created by ChatGPT. But for me, the worst part was that not only was he making a low effort to provide me a feedback, but this person who has spent 20 years in IT tech was calling me sir. Like, sir, was I ever knighted by the Queen or the King of England? Probably King Charles had knighted me, and I didn't know about it. I wanted to go completely ballistic on him. Sissifications. But then I thought, hey, this is great. Since frankly, maybe I don't understand what all the feedback that he has given, but maybe I can use an LLM to answer him and actually create something great, think big and evolve. If you actually look at it, the essence of the entire set of 1,000+ words that I received, it can be brought down to a few points, which basically revolves on the fact that I had shared a fine-tuned LoRA and not a GGUF model, which can be easily deployed. But this actually resolves 3 out of the 5 points that he had mentioned. And there were other 2 points which are based on language inconsistency and crop context conflict. Now, those are big words, but we'll try to solve it. And I want to make this openly available, since agriculture in India has a business model problem. During the Impact Summit, we had published a case study in agriculture compendium, and I had the opportunity to interact with many industry stalwarts. One of them mentioned that he was spending 17 cents for each message that their LLM-enabled bot was responding to. Now, in a country where an average farmer earns 24 cents per day, that is a big problem. And I'm not making up these statistics. This has been said by the National Statistical Society of India. But that's why in India we need new ideas and business models to solve something which is unique to us. But the idea of making this open source was that people take and build something on top of it. And probably they will remember me for that. So who are we to do this? ThinkEvolve is an award-winning AI startup. We have helped our clients in healthcare, agriculture, financials, and security and defense to implement cutting-edge solutions and improve their workflows. We have been winners of the Economic Times Digitech Award, Telangana Grand Challenge, Norwegian AI Row Challenge, and the European Space Agency Challenge. Some of our research has been in the area of LLM safety and security, along with patents in computer vision under low-resource environments. So do like and subscribe to us, and we love such kind of a contract hits. So in the rest of the video, I will try to resolve the feedback, and hopefully in such a way that you do not need a codex subscription to implement it. One major concern that was highlighted was in terms of deploying the model. This was because I had shared a fine-tuned LoRA and not the whole model. So let's see how we can do that. But we will do one extra thing. We will also host this via web app. And while we are at it, why not also try to do it on a mobile application? I always start by first thinking about my deployment strategy. Because the original model was trained on a Gemma3n 4 billion parameter model. But if I want to deploy it on an Android device, or I or even on a web browser, I need to keep it less than 2 billion parameter in size. For deployment on a mobile app, there are multiple options. One of the method is to use MediaPipe. Another is we can directly use the GGUF by compiling Llama CPP on the mobile. This allows us to directly use an existing fine-tuned model on an Android or an Apple phone. Check out the video. The link will appear somewhere on the top left. Since January 2004, the central government has been running 21 Kisan Call Centers. These cover all the state and union territories in India. They have call center agents who are known as FTAs, who are graduates or above, including PhDs or doctorates. They reply to user queries in their local languages. And if these FTAs cannot answer the question, it is escalated to a subject matter expert from the State Agriculture Department, ICR institutes, KVKs, or from the local universities. This call center is available from 6 a.m. in the morning to 10 p.m. in the night and has a single toll-free number, making it easily accessible to the farmers day and night. It is from this data the government has created the Kisan Call Center logs, which are available on AI Kosh or the Indian Data Repository. This dataset has 44 million records, with the largest set coming from Uttar Pradesh and others spread across all the 28 states and union territories in India. What I like about the dataset is that it has a crop and season tag, along with the query text and response. This gives us a good granular information from the field level. So should I train the model on all the data? Let's see what the experts say about it.
So I've heard that data is really important for tuning models like Gemma, but how much data do I actually need? Like 1,000 records?
So it's going to depend on your use case. In our case, we got away with just 8 examples, so it might not take as much data as you think.
Check out the full video.
So the recent LLMs are very powerful and they have been trained on large scale data sets. So when you want to do a zero-shot learning, 8 data points make sense. But when we are creating a specialized model, we probably require more data points. So what we will do is we will create a data set which has a sampling from across all the states in India. The strategy used for sampling could be more sophisticated. Like if you are training for farmers planting coffee in Kerala, that model doesn't require data from rice farmers in Uttar Pradesh. In the same way, if my model will be used only by farmers in Punjab, I can reduce the dataset to include queries regarding wheat farming or create a subset of all the queries from that state. However, let's remember that fine-tuning a model is an ongoing process. It's not something that you do it once and deploy it. You need to continuously monitor it for data drifts. But the main point over here is that the model should be able to respond to users in their local language. That is the critical point. Let's now listen to what experts say about training these models on local data sets or on local language data sets.
So do you have any advice on tuning a Gemma model to operate in another language?
좋은 예시 데이터를 사용하는 것이 핵심입니다. 대상 언어로 다양한 요청과 응답을 준비하세요. 또한 존댓말 및 예의 바른 표현과 같이 문화적으로 적절한 세부 사항을 보여주는 예시를 포함하는 것도 중요합니다.
Check out the full video.
So I don't understand that language. And if you know what language it is, let me know in the comments. But what the expert is saying is that we need to have a good variety of prompt response pairs in our target language. And these response pairs should also be culturally appropriate. The good thing is that Gemma is itself can natively respond in 120 global languages, which includes Hindi, Marathi, Gujarati, and Bengali, along with other Indian languages like Tamil and Telugu. That, I think, gives us an unfair advantage. Another big advantage for us is the data set. Let me just open it so that you can get a better context. This is a sample of the data set taken from different states. If you look at it closely, and I've also spoken about it earlier, the queries are taken in the local language, and the FTA also responds in the same language, which means that this data set is natively available in Hindi, Marathi, Gujarati, Telugu, or any of the other 22 major languages which are spoken in India. That we have covered our bases, which includes selecting the model based on our deployment requirements. We have checked what is the parameter size that is required to make it run on a mobile app as well as on a web application. The second point that we looked at was curating the data to meet the requirements of our target customer segment. And we have seen how the choice of a model helps us train a multi-language model. At the same time, our data set is in multiple Indian languages, and hence, by taking a stratified sample, we can create a beautiful model. Okay, cool. Now that we have our basis right, let's move on to the training of the model. So I forgot that I didn't give you a walkthrough of the code for our data curation process. So this is our script, which downloads a stratified sample of the KCC dataset. We will first define our total target sample size. Say it is 100,000 records. Now, the first thing that the API does is that it probes it to get a total record count. This is used to compute each state's share of the grand total. Now we don't simply start calling the API and picking up the first page, but what we do is we pick a random starting offset so that the sample is spread across the data set rather than just always taking from the top. This then fetches the consecutive pages from that offset until the state's quota is met. And we then loop through all the states and create individual sample files, which are then combined to create our combined data set. So here we are defining some of our constants. This includes the resource ID for the KCC dataset. This can be accessed from the AI Coach platform. You can give your API key over here. This definition can also be via the environment file, but here we are doing it in the script itself to make it more simpler. The target sample size is a total size of our training data set. We have kept it at 100,000 or 1 lakh units, and all the other states will be now in proportion to this. Right. We also keep it as random offset. It's true. This ensures that we are not just picking up the data from the top of the data set, but we are taking random offsets to capture the data points. The rest of them are related to having ensure that our API calling experience is more smoother and we can take care of any kind of errors that occur. We have also defined that all the states that we need to download, but as I have discussed earlier, this can be changed based upon our target customer. If we are planning to deploy it in only Punjab, we can simply download the data sets for the state of Punjab. And now we have some helper function, but the main magic happens out here. It starts from here because everything is magical. We first start by making the session, and this helps us start the session between the AI coach dataset database and our script. We then enumerate through each of the state, get the total number of records for that state, and then we call the allocate sample function, which determines the total number of records that we need to gather for each of the states. The function does ensures that we maintain the state's representation in our sample as compared to the total data set. Now that we have run and downloaded our sample, we will check the distribution. So this is what our distribution looks like. We have collected about 100,000 samples, but unfortunately we notice that Jharkhand and Tamil Nadu do not have any data. Now, why is this? Let's go back to our original KCC dataset state level metadata. Here you will notice that in the original data set also we don't have anything for Jharkhand or Tamil Nadu. Now this is very critical for us because if we don't have any data from Tamil Nadu, we are probably missing out on Tamil language data sets. Let's go to the Indian Council of Agricultural Research, that is the ISCR website. Here you will see that Tamil Nadu, the cultivated area is around 36% of the total area, and their major crops are rice, cotton, groundnut, mung bean, urdu, and sugarcane. I have also created metadata on the basis of crop, and we see that we do have this information. We have paddy, which is rice, we have urad dal or black gram, we have green mung bean, and we also have groundnut, we have cotton, we have sugarcane, and mangoes from Tamil Nadu are also famous. So we'll also capture this data. So now I have downloaded some of the crops queries, and then I translated them into Tamil language. For this, I used a Google Translate option. All the scripts for this purpose are saved in a GitHub that I will share with you. The dataset is now uploaded to HuggingFace, where you can see that I have divided into a train and test dataset. The test is some data points which will not be used, and to benchmark it with the previous iteration of the model. The train has about 110,000 rows of data which will be used for fine-tuning. For our fine-tuning, we are using Gemma3n E2B billion active instruction model. This is a gated model, so if you are doing it for the first time, you'll be asked to fill a form, but access is granted instantly once you fill in your details. The Gemma3n is a multimodal model. That means that it understands audio input and as well as visual and text inputs. It also has Matformer architecture so that you can reduce the number of compute cost as well as response times by selective activation of the model parameters. The model also has conditional parameter loading, which allows us to bypass loading of vision and audio parameters of the model. This reduces the total number of loaded parameters and saves our memory resources. It also has wide language support and a 32,000 token context, which is quite enough for our use case. I will be using Google Colab for our fine tuning. I have attached an A100 GPU which has around 40 GB of RAM. We have also a system memory of around 84 GB with a disk space of 112 GB, which is quite good for our use case. We start by first installing the required dependencies. I will now attach my Google Drive. This will allow me to save the model weights on my drive, and this ensures persistency across sessions. My drive is mounted. This appears as mounted because I have run this code block earlier. We will now also gather our HF token, which is saved within the secrets which is attached to this notebook. I will now define the configuration settings, which includes the base model, which is the Gemma3n effective 2 billion parameter instruction tuning model, instruction tune model, and our dataset repo, which is a KCC sample 100K, which I had shown you earlier. We will also define what is our output directory and which directory we want to save it, and this is push repo ID. Note here that I am saving the LoRA, the train LoRA over here. The GGUF conversion will be shown separately. I'm going to use Onslaught library out here for fast fine tuning with less memory. A complete installation guide for installing Windows on your local machine is given at the top. I've also done a full fine tuning example. You can always check that out. Now, Onslaught allows us to use less memory for fine tuning, and it also provides us base models. These base models are specifically designed by Onslaught for 4-bit quantization. So I'm going to load that, and I also say that the D type is none, which allows the Onslaught package to auto detect the type of GPU that I'm using. If I'm using a higher GPU or a newer version of it, it will load the B16 weights. But if I'm using some lower type of a GPU card, it will load the float 16 weights because it allows for 4-bit quantization and reduces the memory. We are also not doing a full fine tuning, but we are training a LoRa adapter, which will come up in the next step. Now that the model and tokenizer has been downloaded, we can see out here that it has detected the NVIDIA A100 GPU, which has about 40 GB of memory, and it has decided to use the B float 16 weights. So once this is downloaded, I defined the LoRa adapters out here and then grab the chat template that we'll use to convert our data set into a format which Gemma expects for training. From there, we load the dataset, format the prompts, and finally set up the SFT trainer. I go through all this in detail in my other fine-tuning videos. I'll drop the link at the top if you want the full breakdown of each step. So at this point, everything's set up and we can just go ahead and kick off fine-tuning. So let's start the trainer. Since I'm training for about one whole epoch, that will take about 6,844 steps, and typically on an A100 it takes around 6 to 8 hours. The training loss will typically reduce with as we go training and more number of steps, and it should go below 1 in most of the cases. So I have run one epoch of this, and it took me around, of course, about 7 hours to complete it on an A100. And post the completion, what I will do is I will push this into a repo, the LoRA model. Now, this is not a GGUF. Okay, I need to convert it to GGUF using Llama CPP. So let me show you how I can do that. Now the fun part here is that Gemma3n has a unique architecture. It not only uses Matformer, but also uses multimodal processors for audio and vision. These cause the unslot inbuilt GGUF exporter to fail, and we have to default to convert it manually using llama.cpp. If you miss out these things, you can fall into a deep trap which takes a few hours to resolve. But I am there. I have fallen through those traps, and I will handhold you through the conversion process. So, but let's first start by installing the required packages. Another big failure zone for us is the environment dependency. The latest Torch pulls on Colab uses version 13.0, but our dependencies are compiled on version 12.8. This mismatch will actually throw different looking downstream errors, and they can be quite confusing for the layperson. But let's first, since we have completed our install, we'll restart the session so that our packages are active. Looks like our packages have the correct version, so that we can go to the next step and define our constant variables. Here we are defining the two variables such that while converting, we do not default to using TensorFlow, and also unslot doesn't use Torch AO for our purpose. The adapter repo is defined, which is basically where we have stored our LoRa fine-tune, and this is our base model. After defining our LoRa repo and the base model, we then define the quantization type that we want to do it. Q4KM is basically the newer version of quantization, where each weight is stored in 4 bits. In this block, what we are trying to do is load our base model, which is the Gemma3n model, and it is approximately around 10.8 GB in size. This is loaded into the CPU or the regular RAM, which is more safer for our merging process that is going to take place in the next step. We use the above try exception to load the correct model class for our library dependencies. Okay, now since the base model has been loaded, this is where the key part takes place. Here we are taking the LoRa and baking it into the base model. This is then saved, and the combined model is known as the merge model, which is saved into the local directory. We then also take the transformer, take the tokenizer and save it in the same directory. After all these processes are completed, we will free up the memory by deleting the cache and the model which is in the system RAM. After the merger is completed and the memory has been cleared, we'll do a sanity check out here to ensure that all the file that we have saved is available. As we can see now that the model saved tensors are around 10.87 GB in size, which is the correct size expected from the merged model. We'll also check if we have any empty shards. As you can see that the weights are correct and we do not have any empty bytes out there. So that gives us the green light to go to the next step. Now that we have done our sanity check, I will download Llama CPP and install it locally. Once you have done it, don't forget to restart the session. Now that Llama CPP is ready and we have restarted the session, I load back the configurations to ensure that our base repo quant type and everything it understands, and I run the convert HF to GGUF script. This does the conversion, but note this is for the BF16 model, so we are converting it to the GGUF but in full quality. This is like the master copy, and since this is a master copy, it will be of full size, which is around 8.89 GB in size. The next step is to quantize it. For that, we will download the pre-built Llama CPP binaries for this and use that for the quantization process. If the binaries are not possible, we'll build them up from source. Now, this is a very big step. Here, we take the big full quality GGUF and squeeze it down to the chosen size. This produces a much more easily shippable model. You will see each of the layers being quantized, and finally we have our GGUF, which is 3.3 GB in size. This is close to about 1/3 or around 30 to 40% of the original size of the model. Since we are in collab, we want to do a persistent save of a converted GGUF, so we save it on our drive. I've created a separate folder for that, and you can also download it from Colab using the files.download command. The next step is to log in to HuggingFace with our token and create a new repo and push our GGUF over there. So we upload it to HuggingFace and it's available for everyone. And I got so carried away with that I went out and trained 5 different models across different model families: Llama 3.2, LFM 2.5, Quen 1.7, and Quen 0.6. Once these models are created, I can pull it out into a Gradio app or any other web UI that you are comfortable with. I'm running this on a local commodity GPU, and it gives me token speed, the generation token speed between 8 tokens per second to around 35 tokens per second. Since this is a quantized GGUF, I can also run it on a 4-year-old Android. The link to the full video is given in the description, and a link should appear on the top left. Even though this is a 4-year-old Android device, I get a prompt speeds of around 53 tokens per second and generation of around 4 to 6 TKS. So how good are the models? So we had kept a test data set. I use a sample of that to create a baseline and then evaluate it with the fine tunes. On 2 different parameters, which is the cosine similarity as well as using deep eval, which calculates the semantic similarity of the generations with the ground truths, we see a considerable improvement on the output. We did cover a lot of points in this video. I showed you how your deployment strategy will affect the choice of the model. how to go about curating the data and validating it. Next, we fine-tuned a LoRA for a selected model and then converted it to a GGUF. This was then deployed on a web application, and we also saw it working on a mobile. I followed this up with benchmarking the output. I hope that this helped you understand the entire fine-tuning and deployment pipeline. If you have any queries, drop it in the comments and I will try to answer them. Thank you and have a great day.